This video will be part 3A of this WR-50C series. In part 3, A and B, will be a two-part, we'll look at the modulation provided here when this switch is set in the sweep position. In any of these positions, any of these 6 lettered positions, and these 2 fixed frequency positions marked sweep, it is different. You notice I have the range switch set to C, so I'm still outputting a 1 megahertz signal, 1000 kilohertz. But I have the modulation switch set to sweep. Sweep is another internal modulation. It's actually 2 modulations, but it has an AM component. If we take a look at the oscilloscope, we can see the modulation envelope here. The envelope, of course, is the outline of this yellow area. The RF being modulated is this infill here. You'll see that there's a series of pulses, bursts of RF. This is almost like you would see in a radar transmitter, except in a radar transmitter these bursts are smaller and the interval's a little larger. Let's review how the internal, that's when the switch is set down here. This is the modulation switch, internal, external, sweep. Let's pretend it's set to internal. Where does the modulation come from? Well, these 2 transistors work together to form a 600 hertz nominal sine wave oscillator. The output from this oscillator travels up here, down here, and is applied across a potentiometer. Some amount of this 600 hertz signal is transferred up here. Switch is set in this position. That means these 2 are connected. Comes out here, up here, and the modulation signal is applied to this capacitor, which in turn takes it over and puts it across this resistor in the RF amplifier, thus causing an amplitude modulated signal to be generated. So that's how we generate internal 600 hertz modulation. And we can vary the level of the modulation by varying this potentiometer. We saw that in part 2. Let's put this switch in the sweep position. In the sweep position, a sample is taken from the secondary of this power transformer, right here. Now, this is not rectified. This over here is DC, but this is AC. This center tap is grounded. I don't really know what the voltage is here, probably about 25 volts, 20 volts. In any event, some of this 60 cycle or line frequency, because this is powered into the power line. So in the United States it's 60 hertz. Some 60 hertz signals tapped off here through a potentiometer, up here, through a wave shaping circuit, a 1K resistor, a Zener diode, is out here, up here, and does a little round the ring comes out here and is applied to this capacitor and continues on its way to make an AM modulated signal. So a 60 hertz in the United States, 50 hertz in Europe signal, it's a sine wave. It's shaped, and then it's applied to the RF amplifier, giving us this output. Now the fact that this is taken from the 60 hertz line voltage sample means two things: 60 of these pulses a second, and it's referenced to the power line. There's lots of things referenced to the AC power line. Hammond organs, wall clocks made in the 70s, 60s, black and white monitors, closed circuit television motors in the 50s, 60s, and 70s. All of them used line sync because it's available. We didn't have much battery powered equipment back then. And most sweep generators of that era were synchronized to the power line. Looking at the scope, if I look at the triggering system, I'll get the source of the trigger, and you can see, I'll turn on channel 2 here. I can source a triggering signal from channel 1 or channel 2, external. There's a BNC connector called external trigger, or the AC line. Every analog scope I've ever owned has had an AC line trigger source. And this scope, which probably was designed 10 or 8 years ago, sure enough, it has an AC line triggering source. Now that's probably not true if you've got a USB powered scope or a scope that's powered by a DC wall wart. That means I can synchronize the oscilloscope without any external connections between the sweep generator and the oscilloscope. Since the sweep generator is triggered at 60 hertz, or line frequency, I can trigger off the line frequency and everything is kosher. Whenever we put the generator in the 10.7 megahertz or the 455 kilohertz positions, I'll try 10.7. We still get the same burst pattern, but unlike before, infill now is 10.7 megahertz nominal, but it's sweeping back and forth. What that means is the center frequency is probably 10.7 megahertz. In other words, this center is 10.7 megahertz. This is probably a megahertz less, and this is probably a megahertz more. In other words, the frequency inside this envelope starts at some low frequency, say 9.5 megahertz, 9.7 megahertz. And within the envelope, it sweeps up until it gets to 11.7 megahertz. Every burst comes with a sweeping frequency inside of it. Let's take a look at why the frequency in the 10.7 and the 555 kilohertz setting is varying. Well, we'll go back to the power transformer, and we note this wire comes off here, down here, across to here, up here, to a potentiometer called sweep linearity. The output from this potentiometer tap is applied to a varactor diode, which is really a diode whose capacitance varies with the reverse voltage applied to it. The reverse voltage applied to it is derived from a tap on the AC line transformer. Now this tap's on the secondary of the transformer. It's on the other side of the transformer from the modulation tap. So this modulation, frequency modulation, occurs at 60 hertz at an inverse side of the AC sine wave. Now this varactor diode is only in position in positions 7 and 8. Position 7 is a 10.7 megahertz. It's a 455 kilohertz nominal frequency. That's positions 7 and 8. In all other positions, this capacitor, 10 by 330 microfarad, this is the variable capacitor that's driven by the frequency setting dial. But in the position, in the sweep position, the capacitor is really this. So the capacitor is varying in capacity 60 times a second. It goes up and down, coinciding with the burst of energy in the AM output. So what's happening here is we have an AM signal it's repetitive, contains an RF inside the envelope, and the RF is varying from some low to some high frequency, with the center frequency being either 10.7 megahertz or 455 kilohertz. So the situation is we have a repetitive AM signal containing a variable frequency. Starts low, ends high. So this is a combination AM-FM modulation scheme. In order to understand what's going on here, we need to be able to extract or demodulate the AM signal. That is the AM portion of the signal. So this is a depiction of a modulated, AM modulated RF signal. These little vertical lines in the middle here, going up and down, represent the RF. These sinusoidal peaks and valleys indicate the modulation applied to the RF. Now to look at this on an oscilloscope, we need an oscilloscope that can reproduce the RF. So if this were 100 megahertz AM modulated signal, we would need a scope with a bandwidth of at least 100 megahertz, preferably 200 megahertz. If we extract or demodulate the information by using a detector, we can derive the original modulating signal and display it here. Let's assume this is 600 hertz modulation. Well, we've extracted a 600 hertz sine wave. In order to display this adequately, we need a scope with a bandwidth of what, a half a megahertz? After all, this is only a 600 hertz sine wave. Let's look at the oscilloscope once. Here is an RF signal from the generator modulated with its internal 600 hertz oscillator. I'm going to turn on a demodulated output. So there is the sine wave that we've extracted from the modulated signal. I demodulated the signal with what's referred to as a crystal probe. It's actually just a diode, a couple of resistors and a capacitor. The modulated signal is here. The demodulated signal is here. I built this little circuit on a breadboard. There's an input capacitor here. That's this. That's to prevent any DC that might be applied here from reaching the crystal or reaching the diode. This article was written a number of years ago, and it can be found in the subdirectory. And a couple of resistors. Here we have at the bottom in yellow the output from the 10.7 megahertz oscillator being swept. And in the violet above, we have the demodulated signal. So in part 3B, we'll see what we can do with this information.